So down here, this is the week 4. DW is going to be gone to Chicago. So it's the Parks Cleaning Conference, which is part of the International Machine Technology Show. And it's the Chicago Convention Center is like 4 times bigger than the George R. Brown. So if you've ever been there, it's enormous. And we're having a parts cleaning conference next to the Machining Technology Show. And we'll have a whole day of like 2 tracks, like 24 talks or so. And so I'm introducing the speakers, and it's going to be great. Yeah, so it'll be fun. EPA will be there, and so it's going to be a great time. But let's talk about you guys. So I didn't want to lose this review. I mentioned this last time. I made a couple of videos. So if you go into the week 3 folder, so this week, go into the week 3 folder, you'll see down at the bottom, Exam 1 Review Part 1 and 2, Quiz 1 and 2, Part 1, Quiz 1 and 2. And then notice here, this third one is hidden until after September 10th at 11:59. So as soon as you turn in Quiz 3, at that, at 11:59 that night, this video will pop up that tells you how to do all the problems in Quiz 3. Okay. And then that'll help you study over the weekend and everything to get ready for Wednesday's exam. Sound good? So don't show up at 11 on Monday. Nobody will be here. Okay. Just watch your videos on your own time. Get together with your study groups. The TA or ATA of mine for PCHEM, she's going to come and proctor the exam on Wednesday. So what do you get to bring to the exam? Your TI calculator, pencil, Scantron, the 882 form. Go to the syllabus. There's a picture of it in there. So go check the syllabus again just to make sure you have everything for the exam. You will have an equation sheet. The equation sheet that you get to use is in this video. So you'll see it. It has all the temperature conversions, it has all the pressure conversions and volume conversions, and it has this Clausius Clapeyron equation. And we're going to do a lot of algebra today, and I went ahead and put all the different forms of an equation on the exam on the equation sheet. So you can I'm testing to know whether you know which one to use, okay? Not testing how fast you can do algebra. Okay, so I could have done both on those problems. I chose to go ahead and just let you select the appropriate equation and put in the numbers, okay, as opposed to starting with the parent equation, doing the algebra first, and then plugging in the numbers. Okay. Any questions before we jump in to the material? Yes? Yeah, periodic table. So on the front and back, the periodic table on one side, the equation sheet on the other. Yeah. Yeah. And the exam, you will have to write on the exam because there's a written part. So put your name on the exam. You can tear it apart if you need like place for scratch paper. So it's just one-sided. You tear apart the staple, and you can, like if you're working on problem 6 and you want to use the back of the first page to do your math, that's fine. Because trying to squeeze your math in underneath the little multiple choice places, it gets, you can make a mistake if you don't have a lot of room. So go ahead and use the back of the pages for scratch paper. Just put your name on every page so that I can look to see. So that's the exam. Pencil, Scantron, calculator. That's all you need. Okay. All right, so today let's jump in. We're going to do all of these calculations with vapor pressure and enthalpy. Yeah, and this is the most complicated but the most useful equation in this whole course. So we're going to spend the whole day playing around with one equation. Okay. Now, this is the phase diagram. We just studied this last lecture, and we're zooming in on this portion of the phase diagram. So just the vapor-liquid equilibrium region. So on that line, you have 2 phases in equilibrium. You have the liquid, and then the amount of liquid that has evaporated, that is the partial pressure of that liquid, the vapor pressure of that liquid. So this is that equilibrium. If you change the temperature, then the vapor pressure goes up and it follows that line. So if you're looking at that line, that is the vapor pressure curve for a liquid at any given temperature. Now, it's a lot more complicated than the ideal gas law because you've got all of those bonds in the liquid that are breaking as a function of temperature. And so this isn't just like a PV equals nRT thing. This is the Clausius Clapeyron equation. So we've zoomed in to that vapor-liquid equilibrium region. The y-axis is pressure still, the x-axis is temperature. I've got it in two different units. So I've kept atmospheres in Kelvin, but I've also added torr and degrees C because those are used a lot as well. Okay. And this is the Clausius Clapeyron equation. So notice it's got a lot of things going on here. We've got inverted temperature here. We've got the gas constant, enthalpy of vaporization. So we're going to talk about all these different pieces today. And then we have two pressures. So we have like a standard pressure here at a standard temperature, and then a new temperature and a new pressure. So this is the equation for this line right here. Now, what are those P star and T stars? Well, if we pick the boiling point for a liquid, and this is water, so this is the curve for water. So water has a boiling point at 100 C, or 373 Kelvin, and that is when the vapor pressure equals 1 atmosphere. So that's the normal boiling point for water. Notice we don't have to specify 1 atmosphere. If we just say it's the normal boiling point, that's part of the definition. So if you look up the boiling point for a substance, it won't tell you the pressure because the pressure is 1 atmosphere. Okay, that's the temperature at which the vapor pressure is 1 atmosphere. Now, delta H of vaporization for water. There's nowhere on here does it say for water. Okay. Okay. It's 40.7 thousand joules per mole. So it's a lot of joules. And then the pressure is 1 atmosphere and the temperature is 373 Kelvin. Just like in PV equals nRT, we got to use Kelvin for all of these temperatures. So those are P star and T star. So what is the vapor pressure of water at room temperature? So like how much water are we breathing in? I mean, too much is bad, right? You drown. So we're breathing in water. We have humidity. We have vapor pressure of water. We breathe that in. We also breathe it out. Our body is respiring water. And so what is the vapor pressure at room temperature? So down here, we have this blue dot at room temperature. Notice the pressure is much lower. So this is half an atmosphere. We're way below 1/10 of an atmosphere. So we're like in the second decimal place. Something in the second decimal place of atmospheres. So I've color coded it. This red dot corresponds to the temperature and the pressure for our standard temperature and pressure, okay? And then our new temperature and pressure are given in blue. So this new temperature is going to be 298 Kelvin, and we have the delta H of vaporization in here. We have R, so we can put in all of our numbers and we could calculate what the new pressure is. So here's all of the numbers in this equation with their units. Now notice this is an exponential function. This is e to the x right here. And x equals this big parenthesis thing. So I would calculate all of this stuff first and then take that number and do e to the x, e to that number, and then multiply by 1 atmosphere. So you've got to figure out how to do that on the calculator. So go through the notes with your calculator and make sure that you get the right answers so that you know how to do these calculations with your calculator. If you're looking at this and you're thinking, okay, that makes sense, we plug in the numbers and we get this value here, 0.0367 atmospheres. Okay, great, but you didn't do it yourself. So you get your calculator and you do this with, on your time when you're going back through the notes. You can do it now too if you wish, but this is not an easy calculation to type into the calculator. Okay. So what I typically do is I will do my temperatures first. I'll type in 373 and hit the inversion x to the -1 or 1 over x key, and then I hit minus, and then I type in 298 and hit the 1 over x key, and then hit equals, and I get that difference. And then I'll write that number in here. Like whatever that difference is, I'll write that number. So that I kind of have parts of my calculation done, a piece at a time. And then I'll take that number times 40,700, divide by 8.31, and then I'll write that number down. And then I'll take that number and I'll do e to that number. And then I have the e to the x piece. And so I'll do this in like 4 parts, and I'll have that number, and then I'll multiply by 1 atmosphere, and I get 0.0367. So that's how I would approach this problem. Trying to do this whole thing in one shot on the calculator, it's pretty risky. You're going to maybe make a mistake. Yes.
Are we going to look at this with anything other than water?
Yes. Yeah. And so what would change if we had something other than water? The boiling point would change, and so would delta H of vaporization. So we would have a different vaporization number, and we would have a different TP pair for the starred T and P. Yes?
So the P star is always going to be the one atmosphere?
If it's a boiling point that you're using, yes. So like if I'm using a normal boiling point, then the temperature that I found in a table, the boiling point of whatever gas or liquid, would go in T star, and then 1 atmosphere would be P star. Yeah. Those are great questions. Okay, so that's it. We found the vapor pressure of water. What is it in torr? Because a lot of times for small pressures, we use torr. So you multiply that by 760 torr per atmosphere, and you get 27.9 or 28 torr. So that's easy to measure. Our gauges are very good at that. So that's 27 millimeters of mercury. So even if we, let's see, how would we measure this? This would be fun. So if we stick a mercury manometer up to like a flask of water that was frozen, so we freeze the water, it's all ice, and we evacuate the air, pull a vacuum on it, and then hook that up to a mercury manometer. Okay, so it's measuring 0 pressure in the water flask. Then the water warms up to room temperature. It would push that mercury uphill 27 millimeters. So that water vapor would be the only thing in the flask, and it would create a pressure that would push that mercury uphill by 27 millimeters if it was in a U. And you can see some of those little devices in the books. Okay, so let's talk about delta H of vaporization for a little bit. So delta H is enthalpy. You should remember that from Chem 1. I think it was chapter 5 or 7. The heat required to evaporate 1 mole of a substance at a given temperature. So this is the reaction that we use to show that. So we're going from liquid to gas. So water is liquid and it's going to gas. We've basically boiled 1 mole of water, and now we have 1 mole of gas. And in order to get that to happen, we have to put in heat. And I'm just going to give you a tiny little bit of thermodynamics here. This reaction is called the system. And the heat went in, so it's a positive number. Okay, the system. You see how that's a positive number? So the system gained energy. And that's what we mean by endothermic. It brought in heat, energy in the form of heat. And so we have a positive delta H. If we reverse this reaction, then the gas, when it condenses, it gives off heat. It's exothermic, and the heat would come out of the reaction. When it goes past the arrow, it either takes in heat or gets rid of heat. So that's what's going on. If we're going to go from left to right, we have to put that heat in to get it to go past the arrow and become a gas. Okay. And what are we doing when we put in that heat? We're breaking all of the intermolecular attractions, because that's what made the liquid. It was the intermolecular attractions that caused the water molecules to stick together and make a liquid. We're breaking all of those apart. And so this is a good measure of how strong those intermolecular attractions are. If you have a high delta H of vaporization, you have a lot of intermolecular attractions. Okay. And water, in terms of other substances, its size has a huge delta H of vaporization. This has enormous impact, right? This is why it's so difficult to dry your hair in the morning and why to dry your clothes after you wash them. You use an enormous amount of electricity to dry your clothes. And that's why electricity costs money. So it takes a lot of money to evaporate water. And this is important in my area of cleaning, because a lot of companies think, oh, we're going to go green by moving from a solvent process to a water process, because water's green, right? Get rid of benzene and nitro, and you end up with a water process. But when you want to dry your parts, you're pumping in a lot of electricity to dry that water and to boil the water and so on. And so the energy costs for aqueous processes goes way up. And it's all because of the delta H of vaporization of water. So here's the delta H of vaporization from a bunch of other substances. So not just water, we're looking now at other things. And I've color-coded a few of these that are similar, but look over on the far right. We have intermolecular forces. Now, I've just labeled them. I haven't really given you an idea of the magnitudes of each of those. I could have gone and gotten the Hansen solubility parameters, which would be kind of a measure of how big the D and the P and the H are. But still, down here at the bottom, we have hydrocarbons. And a hydrocarbon is just hydrogen and carbon. That's why it's a hydrocarbon. Okay. And there are no OHs. There's no asymmetry or other atoms in here other than carbons and hydrogens. So these are all nonpolar and they're non-hydrogen bonding. So they only have dispersion forces. So let's look at this one that has butane of 58. Acetone is also 58 in terms of grams per mole. And it has dispersion and polarity. And it has a much higher boiling point, almost 100 degrees higher. And it has a higher delta H of vaporization. So adding in that polar component of that carbonyl bond, that carbon-oxygen double bond, has given it a dipole moment, and that allows it to have stronger intermolecular attractions, higher boiling point, even though it's the same mass, higher boiling point, and higher delta H of vaporization. Here's diethyl ether. It has an oxygen in it, but really no OH or NH. So it doesn't hydrogen bond very much. It's just a polar molecule. And it weighs the same as ethanol. And ethanol has the OH. So it's a hydrogen bonder. So it has the DP and H. Same mass, but here another 50 degrees in terms of its boiling point, and another like 12,000 joules more to evaporate. So it takes a lot more energy to evaporate ethanol than it does ether. Okay. So this is sort of the ramifications of intermolecular attractions. And then look at all of these. We have 46 and 32 and 58 masses down here, giving you an idea of how big those electron clouds are. And here's the puny little water, 18. And yet it's higher than all of them. It has a high delta H of vaporization, high boiling point, and everything. Because water is such a strong hydrogen bonder, it's made of OH groups, and so it can hydrogen bond to itself. And that's what makes water so hard to evaporate. So let's say we knew the critical constants and the boiling point, but we didn't know the delta H of vaporization. So it's the same equation, but we just have different knowns and a different unknown. So let's do this problem where we solve for the delta H of vaporization for methane, even though it's in this table already, like we have it in this table, but let's pretend we don't have this table. Okay, so we don't know that it's 8,200. We're going to find out what it is if we know the boiling point and the critical constants, which gives us a temperature and a pressure. So let's do this problem. So if we have a pressure and temperature points, we have two of them, can we find the delta H of vaporization? So we know the boiling point and the critical point for methane. So this is one TP pair or PT pair, and this is another. And notice nowhere in here was pressure stated. It's because it's assumed. If we have the normal boiling point, that's the normal boiling point at 1 atmosphere. So use these two pressure temperature points to solve for delta H of vaporization. So here we get to do some algebra. We start with that Clausius Clapeyron equation. And I'm trying to solve for this guy right here. So we've got to do a couple of things. We've got to get P over to the other side. Okay, so we're going to put it in the denominator over here. And I want to get rid of this e to the x. Do you know how to get rid of e to the x? Natural log of e to the x is equal to x. So if I take the natural log of that, then this whole parenthesis piece comes down. So that's the next step. I have the natural log of P1 over P2 is just equal to that thing that was up in the exponent. So the natural log of both sides, I completely canceled the e, and now I just have the argument that was up in the exponent. So that's just a review of some of your mathematical rules here. And now I'm still trying to solve for this delta H of vaporization, so I'm going to move this R to the other side over here. And I'm going to bring these temperatures down into the denominator. And so that delta H of vaporization is equal to R ln P1 over P2 divided by that temperature difference. Not too bad. It just takes a little time. It's prone to a few mistakes, and so I go ahead and give you this bottom equation on the exam. So if you know you're solving for a delta H because you have P and T pairs, then you can use this equation. So let's put in all the numbers. 8.31 joules per mole Kelvin is the R. Natural log. Okay, let's figure out what our P2s and P1s are. Notice how this T2 is really in that position of the T star, and the P2 is in the position of P star. Let's go ahead and make that our boiling point. So this is T2 and P2, and that means this is P1 and T1. And so now that we've labeled those, we can put them into this equation. So 46 atmospheres divided by 1 atmosphere, natural log, times 8.31. And then I would write that number down, and then I would do 1 over 112 minus 1 over 191, and write that number down, and then I would take the ratio. And we end up with 8,600 joules per mole. That's cool. That's pretty close to 8,200. Okay. And so, you know, why is it different than 8,600? I'll have to show you someday one of the plots that the enthalpy of vaporization is a function of temperature. Okay, so there's not like an exact value for water. It's a function of temperature. So you could have, depending on which temperature pairs, a slightly different number. So let's see how far off we are from 8,200. So the literature value that we had in the previous table was 8,200 joules per mole. And so that's a difference of 400 joules per mole. You see that? 8,600 minus 8,200. Let's divide that 400 by the literature value to see what our percent error was. So we're only off by 5%. That's great. So this, you know, this technique, if you have two temperature points and a pressure, the boiling point and the critical point, then you can solve for that delta H of vaporization with 95% confidence. So it's pretty good. Any questions on this one? We'll change gears again, so make sure you understand what we did here. Yes?
Where did you get that 8.31 joules?
Oh, that's R, right here. So the constant, good question. So R is equal to 8.3145, okay, joules per mole Kelvin. And when we were doing the gas velocity part of the chapter, that turned out to be Boltzmann's constant times Avogadro's number. Okay. But when we were doing PV equals nRT, we wanted different units. And so for PV equals nRT, we were doing 0.08206 or 821 liters atmospheres per mole Kelvin. Okay. And so a liter atmosphere can be converted into a joule by multiplying by the conversion from atmospheres to pascals. So you get 101.325. And if you take 8.08206 times 101.325, you get 8.3145. Okay, so it's just a conversion of units from liters atmospheres to joules through pascals. You get one constant converted into the other. Yeah. So whenever we're dealing with things like this enthalpy is going to be in a joules per mole, okay, then we would want to use the gas constant that has joules per mole. And when we're in an ideal gas law situation where we're dealing with things that have volumes, liters and atmospheres of pressure, then we would want to use the gas constant that has those units. And so it's a context thing. You look at what kind of calculation you're doing and look at the units and say, okay, it makes more sense to use the joules per mole R versus the liters atmospheres per mole Kelvin R. Yeah. Yes.
Both the R's going to be on the,
Yeah. So you'll have them there. Again, I want to give you all the tools. It's hard enough to learn all the chemistry, but also to like turn it into a memorization game where And that allows me to be confident in the multiple choice thing. Like if you got the constant wrong, like maybe you used, you knew how to do the problem, but you used 0.0821 instead of using this one, you get a wrong multiple choice answer, and it was a memorization error, right? Instead of not knowing how to do the chemistry. And so I want to give you all of the tools you need for the memorization piece so that I can actually test your knowledge of the chemistry. Makes sense, okay. Okay, now put your pencils down on this one. I'm just going to show you something fun. What do you do if you have multiple points? Which two do you use? Right? So this is water. It has a triple point, a boiling point, and a critical point. And this is foreshadowing. We'll do this in PChem, but I just kind of show you when you have multiple points, you don't have to decide which two to use. You can use all three and plot it. Okay, so look at our equation. I've color-coded it. This could be plotted where this is y equals mx. And so if I plot these points and find the slope is equal to the delta H of vaporization. Okay, but these are some really weird pieces. For y, I have to calculate r ln P1 over P2. And so I'm gonna label this one as P2. That'll be our standard number, and this is T2. So for all of these, that's going to be P2 and T2, and then I'm going to have y values and x values. So let's calculate the y values. So if this is P2 and T2 and P1 and T1, then the y-axis, this is the natural log of 1, which is 0, okay? If this is P1 and T1, then my y-axis value is natural log of that ratio times r, I get this y-axis value. And the critical point, if this is P1 and T1, I calculate a different y-axis. So those are my three y values. What are my t values, x values? I have T2 here. If I have 1 over T2 and then I treat this as T1, I end up with 0 because they're the same number. If I make this one T1, I get this number. If I make this one T1, I get that number. Okay, so I have my y values and my x values, and I plot them. And look at that slope. It's a nice linear function. I captured 99.96% of the variation in the data points. That's great. And the slope is 41,605. So that's my delta H of vaporization right there. So that's how you use 3 points or 5 or 100. So if we had lots of P and T points for a gas, we could really accurately calculate the enthalpy of vaporization. And don't worry, you'll see this in PChem in 2 or 3 years. But I just wanted to show you what you would do if you had 3 data points instead of just 2. You would just use statistics and calculate this with the average value. Okay, so let's look at the percent error. Our literature was 4,700. The difference between 41,605 and that is 900, and that's about 2% error. So our error improved analyzing using 3 points. If we had 5 points, it would be even better. Okay, in fact, that's probably where that literature value came from, is using lots of points. Okay, so again, this is just foreshadowing. We could take this equation and make it a little more complicated in its analysis, but that's when computers become really useful. Okay, so this now is back to the news report. You go and you look at the news report and they're talking about the percent humidity, and they use this term dew point. And so we're going to calculate with this equation what the dew point is. So remember, the percent relative humidity is sort of this maximum vapor pressure of water. It's the actual divided by the maximum. And so it's really good that we don't always have the maximum amount of water in the atmosphere. Okay, really 100% humidity all the time. It would really be bad. Okay, and so thank goodness we have, less than that often. So if the percent humidity is less than 100% at a given temperature, then there is a lower temperature where that percent relative humidity would be 100%, and that is the dew point temperature. So if you get the temperature below that dew point, then you will cause spontaneous droplets, dew, to form. So if we're sitting here at like an 87 degree day and 50% relative humidity, if we get it below like 65 degrees, then we'd be at 100% humidity. If we go to 64, then we would have dew form. So if we have, in this example, 70% relative humidity at room temperature, what's the dew point temperature? So his same equation, Clausius Clapeyron equation, only now we're trying to dig way in here. We're trying to get to T1. Okay. So we're going to take the pressure 2 over to the other side, take the natural log to get rid of the exponential. Then we're going to multiply this delta H vap over R through. So we're going to multiply it into this and distribute it into that difference. Okay. Now, I've got, this piece equals that piece minus that piece. I can swap these, right? I can add this piece to both sides, and it moves over here. And I can subtract this piece from both sides, and it ends up over here. So that's what I did there. I just essentially swapped positions because I'm trying to get to this T1. And so now I have T1 over here in the denominator. I don't like it in the denominator. So I'm going to bring it over here on top. And I'm going to take this whole piece, divide both sides by that piece, and move it down to the other side in the denominator. So does everybody see what I'm doing algebraically? T1's coming over on top, and that whole piece is going down into the denominator. It just makes a really ugly looking equation, but that's what it is. It is what it is. Okay. So that's the dew point equation. Now, we know T2, that's 298. But where's P1 and P2? What's up with that? Well, look up here. This percent relative humidity is the ratio of the pressures. It's the actual over the max, okay? And so this piece right here goes right in for P1, P2, only not as a percentage. It goes in as the decimal. So it goes in here as a 0.7. That is that ratio. That's the percent relative humidity. So you put in 0.7. We know the delta H of vaporization for water. We're going to use the Joule version of the gas constant. And here's all the numbers. So how would you do this on the calculator? Well, I would go ahead and take this, probably calculate this fraction first. I would take 4,700 divided by 8.314 divided by 298. And then I would subtract, and I would type in 0.7 and hit the natural log button and then hit equals. Again, you want to try this on your own with your calculator. Then I would take that piece, I'd write that number down, and then I would multiply by 8.314. And then that's all in the denominator. And so you could do this two ways. You could do 1 over x times 4,700, or you could divide by 4,700 and do 1 over x. It doesn't matter which order you do those two, and you end up with your temperature. Okay. And so that's 292. So let's put it in numbers we understand. That's 66 degrees Fahrenheit. So that's pretty cool. If we're at a room temperature day and it's 70% relative humidity, if the temperature cools down below 66, typically at night the temperature drops, then they'll be dew in the morning if it gets below 66. If you see the dew point, it's 66, and you think that the low predicted for the morning is only going to be 71, then you're probably not going to have dew in the morning. Does that help explain where dew point comes from? It's that temperature at which the relative humidity becomes 100%. If you go below that temperature, then you've got more water in the air than needs to be there, and so that water starts to come out and spontaneously form droplets. Yeah. So that's pretty much everything we've got for this course. This first exam piece is calculating all the way through to the dew point. Okay, so this is the take-home skills that I want you to have, and these are the last 3 problems on the quiz 3, is one of each of these. Use the Clausius Clapeyron equation to solve for the vapor pressure at room temperature if you're given the boiling point of a substance, and it's delta H of vaporization, so you need that too. Okay. And then understand what makes delta H of vaporization large, like those intermolecular forces. You should be able to estimate the ranking of molecules. So things that have OHs, like alcohols, should be above hydrocarbons. And the smaller the molecule, the more significant that OH will be. So like methanol would be above, say, like a really long chain hydrocarbon with an OH. And then the Clausius Clapeyron equation with the boiling point and critical points to find the delta H of a substance. That's on slide 9. And then if you get the relative humidity and you know the delta H of vaporization, you should be able to solve for the dew point temperature. Okay. We're done way early, so let's take some questions. I can give myself some scratch sheets and we can take your questions. Let's do that.
I just have a random question.
Okay.
Can you go back to the table with the delta H?
Yeah, absolutely. Scoot right by. Oh, right here?
So, yes.
Great.
So you said that hydrogen bonds with nitrogen are they as strong as oxygen?
They're not as strong, and I'm concluding that from this picture or from this table, because you look at ammonia, it has 3 NHs. It should be a really strong hydrogen bonder, but it doesn't have. I mean, it's a little bit more than half of the delta H of vaporization of water, and that's not they're not that different in terms of their masses. So ammonia, let's see, it's got 5. 8. So it has 10 total electrons in it, okay? And water, so you've got, it has 10. So they have the same number of electrons. So it's not really a size of a cloud thing that's making water so much higher. It has to be the hydrogen bonding and the polarity too. Could it be what?
Could it be shape?
Well, let me draw them real quick. So water, if we look at their Vesper shapes, it's like this, and it's got the lone pairs up here. And I'm going to draw them kind of one on top, one in front, one in behind, because it's like a tetrahedron. Okay, and then ammonia, that wedge is meant to bring it out towards me, and this dash takes it back inside the paper, and here's the lone pair. So both of them kind of, in terms of their electron domains, have a tetrahedral shape because they each have 4 electron domains. But, ammonia has 3 hydrogens, water has 2, so they take different molecular structures. Do y'all remember the names for these? Water is named bent. It's not one of the strange ones. But what is the one for ammonia? Do you remember what that was called? Trigonal pyramid. Yeah, trigonal pyramidal structures. It's a pyramid, but it's got 3 base points, so it's a trigonal pyramid. They do have tetragonal pyramids, but this is a trigonal pyramid. And it may be that this dipole is stronger than the ammonia dipole, so the polarity could be stronger in water, but it's also the hydrogen bonding. Yeah.
So the trend for boiling point is like the stronger the molecular attraction, the higher the boiling point.
Yes.
Okay.
Yeah. And the larger the delta H of vaporization. And you see, I gave you 3 exact same questions on quiz 3, and I just wanted you to make that connection. The boiling point goes up, so does delta H of vaporization. There's one strange exception to that here, I noticed as I was looking at this. Which one of these is higher? Here it is, yeah. This one. This is a weird one, question mark. The butane has a higher boiling point, but a lower delta H of vaporization. Okay, so that breaks my brain. So don't let it break yours. So this is a question mark. But everything else, the trend, that's the only exception in this table. Everything else, the boiling point's higher, and so is the delta H of vaporization.
So it's like, let's say the chain is longer, would that lower the boiling point?
Yeah, and I think it's the dispersion forces in this floppy chain are larger, and so that allows it to to have a higher boiling point. Yeah. So that's great. So it's a little bit of math, right? All those Clausius Clapeyron things, but it's also the concepts. And I kind of try to find a balance. I don't want you to just memorize a ton of concepts and not be able to do problems, because this is the science majors chemistry course, and science majors have to be problem solvers, not just knowledge knowers. And so if you can't do the problems, you're not going to be a great problem solver. But it's also more than just being math. If you just did math, you'd be a math major. So you got to have the knowledge too. So I try to balance it. I don't know that I get it perfect, but that's what I'm trying to do. There's some knowledge pieces, but there's also some problem math parts. Okay. So good luck. Study those reviews. My thoughts are with you as you go forward to the next week.